Now, what are the node-centric tasks? We will look at it. So, first one is node classification. Now, look at this particular graph. So, I have you can see there are two kind of data types of nodes. One is orange, another one is green, and I have one other node here which I want to actually provide a label, whether it is a green or it is a orange node. In other words, I want to classify these nodes. And when we can use this kind of classification, take an example of social media network where each node is a user and the interaction depending on whatever interactions we decide, whether they are, for example, take off Facebook, each node here is an account, and if particular person is a friend of other person or not can be an age. So, I have two nodes connected by whether they are friends or not. So, I can create a graph. Now, based on that also I can actually have a new node which and I want to know whether this person can be friend of other people in a group or not. So, I can use different users property to classify whether this particular new account can belongs to this kind of group or other kind of groups. And this particular kind of task is prevalent in a biology where we want to assign a protein a function. So, in that case my each node will be the protein and there is a interactions going on which is called protein-protein interactions, and now I have a new protein and I don't know what is its role or role in any function, and I want to assign that. So, can we use properties of protein such as sequence, chemical structure, chemical properties, amino acid motifs act to find out what is going to be this particular protein's function, whether it will has this protein function or this protein function. So, node classification is a very much integral part of many node-centric tasks on the graph. Another one is the link prediction. Now, here I have a set of nodes and I have a new nodes, and I don't know whether there is a link between this node and rest of the nodes. So, I want to predict whether there is a link between these two, this two, this two, or this two, or maybe this or this one. So, here we want to find out whether there is an edge between two nodes or not. If it is missing, using the edge connectivity and the node connectivity available to us in the existing graph. So, again nodes are users. So, connection between existing users and new users can be actually predict. Similarly, in the biological networks there are many interesting applications which we can see it where the nodes are biological or chemical entities. Biological entities like gene, protein, metabolites, and chemical entities like drugs or any chemicals which used in a therapy. And question we can ask is, can we predict between a new entity and the existing entities? There is an interaction. For example, protein-protein interaction we want to predict for a new protein. Gene regulatory interactions we want to predict. Drug-drug interactions sometimes we want to predict, particularly understanding the side effects and those aspects. Drug-disease interactions we want to predict, whether new drug will be effective in a given drugs based on the past drugs which have been effective on these particular diseases. So, link predictions is another problem which are widely used when it comes to node-centric tasks, where node is used as a data and we want to find out as a edge between any set of two nodes. Third one is the interesting node based task is called community detection task. If you look at this particular graph, I can actually see I can actually create cluster of these three types of community. Correct? So this is a set of nodes together, set of nodes together, set of nodes together. Now, community detection is one of the important question in social media networks as well as biological networks. In social media network, again, nodes are users, and question here we are asking is a subset of nodes or modules with common property. Here, by looking at them, I have decided that there are three communities. There might be other way we can actually figure it out, the communities. And here again we are going to use node or nodes as a data points and try to figure it out what are the subsets of nodes or modules with the common property. In biological networks, again, the biological or chemical entities are nodes, and they can represent as nodes, and the interactions are depending on whether they interact together or not. And what we want to actually figure out a group of proteins or modules for a specific function or specific task in case of metabolite in the reaction pathway network. So there are set of metabolites working together for accomplishing a particular task. In that case, I want to find out what are those set of metabolites which are acting in a particular or specific task. So in that case, I want to do the community detection. Community detection can go larger than the just simple biological networks, but also a community of microbes and etc. So here again we are going to use node as a data point and then figure it out the different communities. Similarly, graph-centric tasks are also widely used. Graph classification and regression is one of the main idea. As I mentioned earlier that in a graph-centric task, I have a set of graphs with the labels. Here I have given two examples. I have one graph with the label yes, another graph with the label no. Here we are using graph as an input with a label. And the question we are asking is, can I actually predict label for a new graph? Let's take an example. For example, property prediction. In a drug discovery, property prediction is one of the challenging problem. The objective here is, given a molecule, I want to predict properties such as solubility, toxicity, antimicrobial property, etc. Now, I have a just molecule which I can represent as a graph. Actually, I showed you earlier. Atom as a nodes and the bonds as a edges. And I have already database where particular molecule has a particular kind of application. For example, antimicrobial property, I know that set of molecules and their labels, whether they have antimicrobial property or not, yes or no, yes or no. Now using this data, I want to build either a classification or regression task where when I get a new molecule or I come up with a new molecule, I want to know whether it has an antimicrobial property or not, or whether it is soluble in certain solvent or not, or it poses certain toxicity effect or not. Those kind of prediction I want to do. In that cases, my chemical structure of molecules are input, and I represent each of these chemical structure as a graph. And the question we are asking, as I told you, is what is the property of new molecule? In other words, what is the label for this molecule given this data available to me? Here each molecule is a data point and each label is associated with each molecule, and what we are looking for is predicting for a new molecule or new graph what is the label, and that's the graph centric task. So graph classification or regressions are widely used for many application, property prediction is one of the major user of those kind of tasks. Now, we discussed about graphs as a data, and it's important in solving different problems. Now, we have to come to the business, how we can do feature engineering when graphs are used as a data. Why do we need to actually do feature engineering? Because we need to know how to represent a node or graph so that features can be sent to the models and model can be trained. And as we discussed, the computers handle numerical features well. So in a traditional approaches, we do feature engineering, which is typically hand designed features such as node degree statistics or graph degree or incident matrix can be used as a feature. And the objective here is, given a graph, what kind of feature should be used, correct? So I have a graph and I want to know what kind of features I can actually use to perform certain task, which can be node classification, can be graph classification, community detection, etc. So let's look at some feature engineering we can do using traditional approaches, which we have learned in earlier lectures, one-hot encoding. In a one-hot encoding, we will have a binary representation where 1 represents the presence and the 0 represents the absence of the node. So I will create a matrix, which is, in this case, I have a graph, I have 6 nodes, 7 edges, and I have created one-hot encoding of each node by constructing node versus node matrix, and the element of this matrix are 1 if this node is present, 0 if not. So here in this particular row, all diagonal element like u, v, w, x, y, z, I have a 1, 1, 1, 1 and remaining places 0, 0, 0. So each row and column gives the encoding of particular node. Okay, this is, you can think of this as an encoding of u, it is an encoding of v, and henceforth. Now, what is the problem with this one? One of the biggest problem is that we never talked about edges, or what is information about connectivity. What node is connected with what, we have not talked about it. And there are a lot of zeros. So sparse matrix. Another one which is famously used in a graph theory is a degree matrix. Degree matrix is a diagonal matrix which contains the information about degree of each vertex or node. So degree is basically connectivity information, how many edges, how many nodes it is connected with. So u is connected with 2, x is connected with 1, 2, 3, v is connected with 1, 2, 3 through, okay. Number of connections for each nodes we have created, and we created a new matrix which is again node by node matrix. It has some information about edge now, correct, because this 2, 3, 3, 3, 2 and 1 provides some idea about what are the number of edges incidenting on that particular nodes. However, it is still a sparse matrix, and we do not have a really interaction between. So I know that there are 2 edges, but which nodes they are interacting with, that information is not there. Similarly, there is an adjacency matrix. It provides little more detailed information about interactions, where pair of nodes are adjacent if they are connected by the edges or not. So same node is, there is no self loop, so 0, with v it is connected, so we have 1, w it is not connected, it is a 0, then x is connected 1, 0, 0. So this particular row or even column provides you some kind of connectivity information also. So we have retained information about connectivity, and sum of each element in the rows or columns gives the degree of each node, which is basically 2, 3, 3, 3, 2, 1, which we have seen earlier. Okay, so this is good choice in some sense. But we also have an incident matrix. The incident matrix provides node edge relationships. So it actually now connects two kind of objects in our class. Here one object is a node, another object is a edge. So it is encodes node edge relationships. So U is connected by A and B, or there are two edges which are actually incident on U. Similarly, V is incident by B, C and D, and henceforth. So incident matrix is also good choice, it looks like, because it provides node edge relationships. Of course, we do not know where the U is connected from directly, but of course we can see that there is a common edge between U and V, so we can actually infer from that. And sum of each column is also here is 2. You can go back and see why it is 2. It's as a homework. But it looks like incident matrix, adjacency matrix have certain features which we are looking for.